powerful, but certainly involves negatives and positives and stuff like that. Or we just think it's false.
I'm legit thinking this through with you too. I don't remember what the answer is, so I'm not just pretending to struggle with it. Gut feelings.
I think I've kind of got a gut feeling about it.
I think it's correct.
You think it's correct?
Yeah.
So what's leading you to think that? I think you're right.
Well, I'm trying to visualize it as like the plane fully over itself.
yeah.
And so like the three possibilities I see is that it's converging to zero, and so that just doesn't affect it. Or it's not, and therefore either all the points that are converging to negative B are now converging to B, or it isn't affected at all.
Yeah, that sounds pretty good to me. Is that what you were thinking too, Kayla?
I was just thinking about the first part of the order limit theorem, where it says that if a sub n is greater than or equal to 0 for all n and n, then like a is greater than or equal to 0.
Yeah.
Which would indicate that it's the same thinking as the absolute value.
Yeah, totally. So, did you have any other thoughts out of this, Anna?
No, I was kind of leading to that too, and I was walking through the proofs for the, what's on page 52?
Yeah. Yeah, that is definitely, yeah.
So let's take a look at that that order limit theorem. I kind of want to make it a little bit stronger, actually, because definitely the idea is in there. Let's take a look at theorem 234. So theorem 234 says the following: so part A of it says if a sub n is greater than or equal to 0 for all n greater than or equal to 0, then the limit of a sub n, assuming it exists, is greater than or equal to 0. This is a very strong statement because look at what it's saying. It's literally saying that all the terms have to be non-negative. But they don't all have to be. They just eventually have to be. So this is like a key point that I kind of wanted to make today, is that we could make this a little bit stronger so that it applies to more cases. So is that the word? Yeah? No? Redux? Not like the chemical one, but isn't this like to redo it? Like,
This is a chemical thing too, right? Like a
Redox?
redux, like, I don't know, I won't
Yeah.
use that. New and improved. So we could say this: if there exists some place in the sequence such that a sub n is greater than or equal to 0 from that point on, then the limit of a sub n will be greater than or equal to 0. In other words, what I'm saying is that it doesn't really matter. When you're thinking about sequences, it doesn't matter what happens at the beginning. Everything we're concerned about is tail behavior, is end behavior. So I could have a sequence like this. Here's my a sub n. Negative, negative, oh, positive, oh, back to negative, Oh, geez, that's crazy. Doing all sorts of shit. But then, at some point, all of a sudden, everything's fine. You know, it stays above 0. It does some weird shit. But this is what I'm saying right here, that there's some point where eventually the sequence acts like I want. And so in the limit, it will then have that same property. So when we come up here, and so this is actually going to combine that idea with what Noah was talking about. And I think, and I always tell you, Michael, to lay off the cases, but I think cases here can be pretty helpful. I'll get this recording up for you as soon as possible, Anna. So for example, we would break this into some cases. If b is greater than 0, the limit is greater than 0, then eventually, at some point, we're not going to write a formal proof, but at some point n, it looks like here's b, right? B is greater than 0. So I can pick a little epsilon neighborhood around this. So this would be b minus epsilon. This would be b plus epsilon. And what if I picked epsilon equals half of b? So that it makes this little epsilon tube here, right? And so if I know the limit is positive and the sequence converges, at some point, the whole sequence also has to be positive at my cutoff. So if b sub n is greater than 0 and the series sequence converges, then eventually b sub n must be greater than 0. Does that make sense, like intuitively? Yeah? And you can see there's a pair. So absolute value of b sub n is going to be is just literally going to be b sub n at that point for little n bigger than or equal to that cutoff n. And the limit's positive, so really nothing has changed. It's just saying that sequence is going to be just fine. No matter if it's alternated or not, eventually this will be cool. So similarly for a negative, right? At some point, if the limit is negative, here's my b, pick a small epsilon neighborhood around that, and eventually you'll be inside that strip. So similarly for b less than 0, at which point the absolute value of b sub n is good, just negative b sub n, and b, absolute value of b is just negative b, and then this is just the algebraic limit theorem, or one part of it, essentially. And then finally, if b equals 0, well then the absolute value of b is going to be 0. I don't know that the sequence will. So this actually, let's see, is this a problem? Because this seems like it doesn't have this nice stuff here, right?
let's see, so if the limit is the absolute value. Oh, wait. Wait, okay, oh no, everything's cool. For some reason I was thinking we were going the other way. So if I've got this sequence converging to 0, let's see if we can argue this out. What's my B sub n? It's definitely converging to 0. Why does the absolute value also converge? Well, let's take a look. Let's see what that would mean in the proof. We might have to get a little proof action going on here, because I'm a little worried. I don't want to make a bold claim, and I don't see an easy argument like this, but what would it mean to have this happen? So we know this. What does this mean? So it means for all epsilon greater than 0, there exists some cutoff such that absolute value of b sub n minus absolute value of b is less than epsilon when n is bigger than. And I just wanted to see this inequality because I was thinking maybe this could help us a little bit. If we could, oh shit. I got a little idea here. So true or false? Absolute value of x minus y, each of those absolute values is less than or equal to x minus y. I kind of think that's true. And if that's true, the convergence of this thing here would imply the convergence of this. And we wouldn't even need all these cases. Does that make sense? Oh, but God, and we even know b is equal to 0. Our limit is equal to 0 here. Right? So let's just take a look in the case when b equals 0. Oh, you guys, I think we're good to go. Once you've got one absolute value on there, you're pretty much set. So check this out. Check this out. So we know this. So that means that for all epsilon greater than 0, there exists a cutoff. Sorry, I keep saying the same damn thing over and over again. We'll call it N1, such that and let's put a 0 here, sorry. So this. This expression doesn't change if I slap absolute values on b sub n. So this expression right here is equal to the absolute value of b sub n minus 0. And so once we actually know the original sequence converges to 0, this is literally equal to that. We can use the same n. And so use this same n1. Thus, this also holds true when we're bigger than or equal to n. And so absolute value of b sub n also converges to 0. I think that's pretty good proof. Check it out. Make sure it makes sense. It's not super deep. It's just like observing that the absolute value of the absolute value is just one absolute value's worth of absolute value. It's a lot of absolute values in a sentence. I also think this is true, and I think that we could have used this for to knock out a whole proof of the entire thing, because, so why would this be true? Think about, you've got two real numbers, x and y. Worst case scenario is their opposite sign, and then that absolute value is the distance between them is a pretty big thing. But if you flip one, if you take the absolute value, so like take x and y, and then look at absolute value of x, which is positive here, and absolute value of y, they get closer. You're moving them to the same side. So I'm pretty positive this is true, and I think the whole proof could just rely on this because, so this is the proof. I'm not going to write the proof out. This is the proof right here, where we just know this. Does anybody not believe that? Because I think I can give you a nice solid proof too. Okay, I'm going to give you a solid proof. Nobody cares.
Well, isn't that just like the triangle inequality?
Yeah, it's some triangle inequality shit. Absolutely, Noah. You just have to kind of tweak it. Let me just write it out to make sure everybody believes me and I'm on solid ground. But if you take the absolute value of x, that's the absolute value of x plus absolute value of y minus x, or equals, whoa. Yeah, yep. That's actually what I mean, yep. That's the way. And then that's less than or equal to this, the triangle inequality, and then subtracting, yeah, there we go. And you can play this in the other direction too. And you can also show similarly that the absolute value of y minus absolute value of x is less than or equal to x minus y. So the result follows from that. Either the positive or negative version of this thing is less than or equal to this, and that's basically what we're saying over there. Cool. I feel pretty good about this. I feel like we're 100% right. We've actually done some proof stuff to bring it. Is the opposite true? So the original implication was this. Is the converse true? They don't ask us this, but we're asking. We'll ask ourselves this. I'm gonna run to the restroom. Perfect time for that.
Yeah, give it value. Yeah.
Any ideas? Michael, you got an idea?
Yeah.
What you think, Fred? True or false?
I'm gonna say false, because I'm using -1 to the n. Because the absolute value of it is always 1. So the absolute value of that, the limit of it does equal the absolute value of 1. Could you write it like that?
Yeah. So wait, say that again.
So the limit of the absolute value of -1 to the n is equal to absolute value of 1, just to write it that way, to keep track of it.
Yes.
But then limit does not exist to break things.
Yeah, nice. Really nice. Anybody come up with any other examples? That's a good one.
I just thought generally that if, just because the absolute value converges like those when we were talking about negative series, sequences, it doesn't necessarily mean that, do you know what I'm saying?
Yes.
Okay.
Yes, yeah. Yes, I do, ma'am. All right, that might be enough playtime for a while. Yeah, this starts getting a little pedantic after this. All right, let's take a look at, let's move onward to a new event. A big theorem for us, really big theorem. Let's actually just prove it today and maybe talk about its consequences. So I'm going to slow down just a little bit until we get caught up. This was good stalling right here. This is worth valuable stall. So first off, do we know what it means for a sequence to be bounded? We're good with that, right? We've talked about that a number of times. So bounded sequence. There exists some M such that and this is the compact version. You could get different lower and upper bounds, but once you know this, you can then decide what those are going to be based on the sup and inf, and gets really good upper and lower bounds. Do we know what this means? Do we know what monotone increasing is? Not 100% solidly. So this just means that if x sub n is less than or equal to x sub n plus 1 for all n. We could also have a definition of this. We could talk about eventually monotone increasing. So eventually this happens. Maybe at the beginning it's like weird and funky, there's no pattern, but eventually the sequence looks like this. Now notice that you can be equal and be monotone increasing, and then you go up, and then maybe you level off and you go up, but you never go down. That's the key thing. Never go down. If we add the word strictly, then this becomes a strict less than sign over here. So strictly monotone increasing would be this beast right here. But we're just, for our purposes, monotone increasing is that. We are monotone decreasing if the opposite happens. So if x sub n is greater than or equal to x sub n plus 1 for all n. And we are just simply monotone. We might not even know monotone if one of these is true. So we just refer to monotone sequences as being one of these two flavors. We don't know. But we do know one really cool thing. That if I have a monotone sequence and it's bounded, it converges. It's an incredibly powerful result. And it's really essential in the study of series. But you never really talk about it in Calc 2 because it's a little too heavy detail-wise for a Calc 2 crowd. I mean, they're freaking out just about doing calculus, so you don't want to introduce this stuff too. So the monotone convergence theorem says the following. If x sub n is bounded and monotonic, it converges. We don't know to what. We're gonna find out what. We're actually gonna build the limit in the proof, but the statement of the theorem doesn't include that. So let's maybe we can work this through together. Got my sequence here, and let's suppose it's increasing. So proof. Suppose without loss of generality, W log, right? That x sub n is monotone increasing.
So,
Yes, sir.
without loss of generality, can it be any increasing, or that it applies if it's decreasing too, but we're just gonna pretend it's increasing?
The proof would have to be redone for a decreasing one with a subtle twist that we'll make a note about.
Alright. So this is true for all x sub n monotone increasing?
Yes, yes, sir. Yes, absolutely. So let's put a little note. We'll handle monotone decreasing with a sentence. Later. It'll just be an observation about the proof that we're about to do. So our sequence looks like this. The first thing we know is that thing is bounded. So since x sub n is bounded, there's some m such that that holds true for all n. Let me be a little suggestive here, mathematically suggestive. So, i.e., the set x sub n, so I'm literally thinking of it as a collection of points, is bounded. What do we know about bounded sets?
They converge.
Well, I
Uh,
don't know about that. I don't think that guy converges, but he sure is bounded.
I don't know that I agree there.
Yes.
Bounded subsets of the reals have soups and imps. Is that what we're doing?
We've got the axiom of completeness. So we know that there's a sup and an imp. See, that might actually be important here, because I know that there's a least upper bound on this collection over here. So by the axiom of completeness, we know that the sup, and let's call it S, equals sup of x sub n, exists. So let's draw it on the picture. There's sup S. How can I show, well, first off, where do you think this sequence converges to? Could it converge to something less than the sup? No, why not, Noah? Yeah, you're right.
Because any number less than, for any number less than the soup, there's some number in the set that is greater than that number.
Level 138, absolutely, yes. So check it out. We know that the limit can't be some number down here, because say that's OS minus epsilon. We know that no matter how tiny epsilon is, there's an element of that sequence inside there.
So look at how the proof is going to go. This is really cool. We pick a little epsilon drop from the soup, and we know that eventually we're in there. Why is everything after that point in there? So this definition of soup gets us in this little strip. Why do we stay in the strip?
The epsilon.
What's that?
Epsilon is.
Yes, epsilon tubes. Got epsilon tube. Why do I stay in the epsilon tube?
Because you're monotone.
Because what?
You're monotone?
Because we're monotone. Because we never drop. So the minute you land into this, you can't go lower. And you can only go up. That's it. So that's the basic idea of the proof. Let's put those together now and make it formal, but that's 100% the reasoning here. So we're going to claim that the soup S is the limit. Claim that this sequence X sub n converges to that soup. Yes, ma'am?
What does WLOG mean?
Without loss of generality. Sorry.
Thank you.
So, and I don't think I need these here, but we'll just claim X sub n converges to S. So we pick an epsilon to do that. We're going to use the definition of limit. Take epsilon greater than 0. How do I get my capital N? How do I get my first element inside S minus epsilon? So we've got S minus epsilon, here's S, and we can think about S plus epsilon. How do I get inside there?
Level 3.8.
Level 1 through, exactly. So, yep. So by lemma 138, there exists some X sub, and we'll just call it capital N, such that S minus epsilon is less than X sub capital N. And we also know this, that is bounded above by S, because S is the soup of the set. So we can't go above that. And make a little note here that this is less than S plus epsilon, because we like to have those full epsilon tubes, right? Just because epsilon is positive. So this is actually superfluous to our argument. Wow. Superfluous, but complete.
See, one of the reasons I chose to do math major is that it didn't involve spelling.
I know, yeah, right? I know, I need to come up with some more basic words. Instead of trying to be all damn fancy in there. Is this making sense, friends? So far, we're following along. Cool. Furthermore, if little n is bigger than or equal to capital N, X sub little n is bigger than or equal to X sub capital N by monotonicity. And now, he's got to fit this inside here. Plus, S minus epsilon is less than X sub capital N, which is less than or equal to X sub little n, when little n is bigger than or equal to capital N. And that is still just an element of the set, so it's less than the soup, which is less than S plus epsilon. So notice that what we have here, S minus epsilon is less than, X sub n is less than S plus epsilon for all little n, sufficiently large. And that's the definition of X sub n converges to S. Right, this is just, the epsilon tube is arbitrary width. I can get inside there at some point evermore, and I'm good to go. So this implies X sub n minus S is less than epsilon on the whole when
enough, thus X of n converges to S. And I think that's a cool proof. I like that we use the soup, kind of pull together a lot of things that we've been doing over and over again. Level 138 comes up every week. You know if this needs any clarity or anything. And let me figure out where I'm going to go next. Oh, we're going to use it with really cool application. Yes. And something will finally make sense. I might have even done this for some of you in a class a long time ago and couldn't justify why it was okay.
What's the little sentence tweak that leads to the
Oh,
monotone?
thank you. Yes, good comment. So, similarly, if X, thank you, Michael. If X is monotone decreasing, use S equals the infimum of X of n, and then proceed, basically. I think it all, the inequalities get flipped, but it's the same argument. And proceed in a mirror-like way. That I've never written in a proof, but I like it. Very appropriate. If I do pat myself on my back. You, good Timmy. Is it okay if I erase? Trinity, you're good? Okay. Kayla, you're good?
Yeah, I just need to write that last sentence.
Okay, gotcha.
Okay, thank you.
Can you read it okay?
Yeah.
Okay, great. All right, so let's, how does this matter to us at all? What's that?
Those are always the funny questions.
Why are we here?
Yeah, yeah.
Why did we show up to class today?
What is this? This is like, every time I meet with my Zen teacher, he asks me some question that, like part of his job is we do these koans, and he asks these questions that cannot be answered, and they're meant to throw your mind into a state of realization. So like one of the big Zen questions is this. Like I spent a whole summer just thinking about that every day, sitting for hours. What is this? Looking at the wall. What is this? What is this? What is this? And another one is this. Who are you? And these questions are actually incredibly profound and have no answers. And the more you search for them, the more your mind just starts to implode upon itself. That's the point. So like anytime we get together, even if it's just casual, and he's like, "How are you?" I'm like instantly like, I'm looking in his eyes, trying to figure out how he's asking me that. He's like, "No, I'm just asking. How was your day?" So anyway, let's get to a question we can't answer. It's one of the nice things about math. Consider one of my favorite square roots. Forever and ever. Infinitely nested 1 plus roots. On and on and on. These don't end here. They look like they end, but don't be fooled. First off, does this have any meaning? If it does, what is it equal to? So, questions. Does this have meaning? Because not everything we write has meaning, even if it looks like it does. 1, 2, if so, and the answer is yes to the first one. If so, what does it equal? Right, so this question of does it have meaning, this was part of Gödel's thesis when he worked on it, when he wrote the incompleteness theorem. Part of it was that if you have a sufficiently advanced language, you're always going to be able to write things in it that cannot be proven true or false. So Gödel proved this, which is just freaking amazing, right? And in the process actually created the idea of the template for the modern computer, because he envisioned this machine that would just spit out a stream of symbols, and it was automated. I don't know why I feel the urge to make this machine more complete here, but it just would randomly type out symbols and generate statements and things like that.
Who's Gödel?
What's that?
Who's Gödel?
Gödel. So you should definitely, here, check this book out. It's a graphic novel. I think there's 2 C's in there. Logic Comics, fantastic graphic novel about the incompleteness theorem, Gödel's incompleteness theorem, and the moment in the 20s when we thought math was collapsing. So all the drama around Bertrand Russell and Whitehead trying to prove mathematics from the ground up. Have you heard of this, the Principia Mathematica? So
That's new.
this is, maybe? Yeah. So Bertrand Russell, famous philosopher, altruist, got locked up protesting World War I. Our involvement in World War I, just a really pretty amazing guy. But he was trying to prove mathematics from the ground up because they ran into something like this. This phrase right here, the set.
Does not contain itself right there?
What's that?
Is it the one that does not contain itself?
Yes, the set of all sets that don't contain themselves. So this somebody proposed this idea. People were just doing set construction like crazy back then. And so this set was proposed. And the question is this set a member of itself or not? If it is, then it shouldn't be. If it isn't, then it is. So that was like, okay, there's something a little wrong with this. Is it okay to just write anything and have it be a meaningful statement? So, so Russell and Whitehead set out to redo the ground and foundations of mathematics from the ground up. They spent a decade writing this book called, this volumes, the Principia Mathematica, where they literally went from basic set theory to prove 1 + 1 = 2, and that took a long time to get to that. And then Gödel comes out, and he's doing this really groundbreaking work that, like I said, I basically gave you the rough idea for it. But his incompleteness theorem essentially said that any logical system that you're going to produce, any language that is consistent within itself, cannot help but have statements inside of it that cannot be given truth values. They cannot be proven true or false. You know, I mean, the most basic is this, something like that. Does that even have meaning? If it's false, it's true. If it's true, it's false. Blah, 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 blah. Does this have meaning? Well, this is, you know, our language is a structure, a logical structure, more or less. And so things like this can appear in any system you have. So Russell proved this, that basically they were wasting their time, that they could not put math on a solid foundation. It was impossible, and they had just wasted a decade of their lives doing that, and he knocked that out in a couple of years. It's really, Gödel's life is really interesting. Back then, he was gay, and he was put into a sanitarium and given like drug treatments to try to de-gay him, you know, because we were so ignorant back then. But yeah, I think he died in a sanitarium. which is just like the little literal creator of the modern computer, and this beautifulness. People are fucked up.
Didn't, what's his-
Turing.
Yeah, Turing also.
Yeah, okay.
he was-
Oh.
Okay, I don't know, I know he was like.
Maybe I am thinking of Turing.
Because Turing was the one who figured out the enigma.
Yes, Turing was the one who was locked up. Okay, Turing.
He wasn't, I think he got, like, I just forgot what that word is.
Well, he was during World War II.
That was World War II.
That was World War II. I'll have to check on my, okay, I
But he
might
was
have
also
just
gay, and he-
fabricated some history.
But he did receive really, like, shitty, like, basically he saved, you know, the
Yes.
Allies, and then they were like, thanks.
Yeah.
Live the rest of your life in solitude and sadness.
That's definitely true.
Yeah.
What I said may or may not be true. It cannot be verified with a truth value, I would have to say right now. Okay, listen, so I just got off on a tangent there. So does this have meaning? Yes. So this is pretty straightforward. To get at this though, we have to think about a sequence. So we get at this by thinking of it sequentially. And what we're going to do is define s sub n plus 1 equals the square root of 1 plus s sub n. So I'm going to do this recursive definition. And we're going to initialize this. Let's let s sub 1 equal 0. And then you'll notice that this does the trick. That s sub 2 is square root of 1 plus 0. S sub 3 is square root of 1 plus square root of 1. And you're off and running. So the way to make sense of this is to think about approaching it in the limit. I mean, taking it all at once just sounds insane anyway. So our question is, does this sequence converge? Yes, Michael?
Can't you do that other trick? It feels like cheating, and I can't explain why. But can't you do that trick where you set the whole thing equal to like x or y, and then that exact? Okay.
But that's pretending, and
It
you're going to
already
see that
converges.
trick emerge from this. But so Michael's talking about a trick where you say, the sum is this, so square it, and it's this, and then you solve that resulting quadratic. We're going to get that same quadratic, but in a valid way. Because this, the minute you do this, you're like, yeah, that means something. Totally, that means something. And then you just keep on doing. So it's like starting induction with a lie, right? Your base case is false or unknown. Build a tower of bullshit. So the question is, does S sub n converge? How can we show something converges in this class?
Show it's bounded in monotone.
There we go, yeah, MCT, right? So use the monotone convergence theorem. So first off, S sub n is monotone. Let's just verify these things. So base case would be S sub 1 equals 0, S sub 2 equals 1. So yep, the base case holds. So S sub 2 is greater than or equal to S sub 1, check. Assume S sub k is less than or equal to S sub k plus 1, so this is my inductive step here. Then S sub k plus 1, maybe I should do this, right? S sub k plus 2 equals square root 1 plus S sub k. And then this is greater than or equal to, oh shit. Oh, that's, yeah, okay, that was a little scary. And then this is greater than or equal to square root of 1 plus S sub k by the inductive hypothesis. And this is literally the definition of SK plus 1. Does that make sense? So the inductive hypothesis came in here. Or the other way. What am I doing? What am I fucking doing? Okay, that. Things are backwards and forwards, but that's all right. So yep, increasing, or monotone, increasing, and then bounded. Claim S sub k is less than or equal to 2. Just pick some clear upper bound here. So S sub 1 equals 0. That's less than or equal to 2. Check. Assume S sub k is less than or equal to 2. And S sub k plus 1 is square root of 1 plus S sub k. And that is less than or equal to the square root of 1 plus 2. And that's square root of 3. That's definitely less than 2. So, yay. So the sequence is bounded and monotonic. Therefore, it converges. Done. So by the MCT, S sub n converges. And now we can claim a limit. Yeah, we got time to do this. So once we've got a limit, sorry, I erased the sequence here, but we know S sub n converges to some S. Our goal is to find S. So take the original relation that said S sub n plus 1 equals square root of 1 plus S sub n. Take the limit on each side. So this is how we're going to get what you were thinking about, Michael. Take lim as n goes to infinity on each side. And we're going to do, there's going to be a little funny business here. Is everybody, this thing still goes to S? It just goes one step faster than S sub n. Does that make sense? Yeah. And then over here, if these are both the same sequence, they must converge to the same limit. So this converges to square root of 1 plus S. And now solve for S. And now we get our buddy back, Michael. Good old quadratic. So solve for S. We get S squared equals 1 plus S. It's S squared minus S minus 1 equals 0. Quadratic formula. Definitely. You're going to love the limit, though. It's so freaking gorgeous. S equals 1 plus or minus square root 1 squared, or negative 1 squared, minus 4 times A times C. Yeah. So 1 plus or minus root 5 over 2. Which one is it? There's two possibilities.
There's only positive stuff in there.
Yeah, so by the limit order theorems, all our terms were positive. We're converging somewhere positive. This is actually negative. So our limit is this. So this crazy thing is this. What is that number? What is that number? That's a special number. It's 5, the golden ratio. Isn't that freaking awesome? This is just so cool. I would tell you, can do it. You might want to do this for fun. I've definitely done this for fun many times, even though I know the surprise.
It's like actual. Oh.
Find that sum, you will find it is phi as well. This is also, and you can use the exact same methodology. Create a recursive relationship, show that the limit must exist by the monotone convergence theorem, then play the game, right? Because this is just S sub n plus 1 equals 1 over 1 plus S sub n. And you start out with S1 equals 0. So you get this. What you'll find is that along the way, you're just getting ratios of Fibonacci numbers. So what you'll see this, that this sum here is the next Fibonacci over the previous. And in fact, another beautiful fact of the world is that ratio also converges to the ratio of subsequent Fibonacci terms. And so the Fibonacci stuff's all hidden in here. So that one's probably a little harder to see. But thanks, everybody. That was a great day. I didn't even know this is where the day was going, but I'm always happy after our hikes together.
Hey, Dr. G.
Yes, sir.
Have you read anything on like I heard them called the metallic ratios?
No.
Well, there's there's the silver ratio, the bronze, and it just keeps going, sigma n.
Oh.
I forget how they're